Dear students, today we are studying Coulomb's law. In the last class, we have studied the properties of electric charges. And the first property we have studied is that the like charges repel each other and unlike charges attract each other. And the force between two like charges is repulsive, while that between two unlike charges is attractive. And this force of attraction and repulsion between two charged bodies can be expressed in terms of Coulomb's law. In 1785, Charles Augustin de Coulomb made a systematic study on forces between charged bodies. And the motivation behind this study was Newton's law of gravitation. And Coulomb measured the electrical attraction and repulsion quantitatively and deduced the law that governs them called Coulomb's law. And Coulomb's law is the fundamental law governing interaction between charges at rest. And Coulomb used a point charges to study the interaction. A point charge is a charge whose dimensions are very small when compared to the distance to another charged body. And the Coulomb's law, it states that the electrostatic force between two point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Let Q1 and Q2 be two point charges which are at rest, and these two charges are separated by a distance r. Then the force of attraction or repulsion between these two charges Q1 and Q2 are represented by the F, and this F will be proportional to the product of the charges Q1 and Q2, and this force will be inversely proportional to the square of the distance between the two charges. Mathematically, the F will be proportional to Q1 Q2 by R square, or it can be represented as F is equal to a constant K into Q1 Q2 by R square. And this constant K is the proportionality constant. And this equation, it shows that a direct relation with charges and an inverse relation with distance. That is, if we increase the magnitude of charges, then the force will increase. But if we increase the distance of separation between the charges, the force acting between them decreases. Here the force which acts along the line joining the two charges. And if Q1 and Q2 are like charges, the force between them is repulsive, and if they are unlike charges, then the force will be attractive. The value of K depends on the medium in which the charges are placed, and also the magnitude of K depends on the unit in which the force and the charges and the distance are expressed. And K has a dimension of force into distance square by charge square. And the dimension of force is F is equal to ml t raised to minus 2. The dimension of force is ml t raised to minus 2. And for the distance, the dimension is L square. And for the charge, the dimension can be written as, that is, charge can be represented in terms of the current and the time. And hence the dimension of the charge will be I into the time. The dimension can be represented as t. Therefore, the dimension of charge is it. Here instead of I, you can consider it as a also. Therefore, the dimension of K can be represented as the force m L t raised to minus 2 into distance square L square divided by I T the whole square. That is, the dimension of K is M L cube T raised to minus 4 I raised to minus 2. This is the dimension of K. And the unit of K, that is, force is expressed in Newton, and the distance in meter, and the charge in Coulomb. And hence, the unit of K is Newton meter square Coulomb raised to minus 2. And the magnitude of K depends on the medium in which the charges are placed. If the charges are placed in free space or in vacuum, then K can be represented as K is equal to 1 by 4 pi epsilon 0, where epsilon 0 is called the permittivity of free space. And its value is given as epsilon 0 is equal to 8.8419 into 10 raised to minus 12 Coulomb square, Newton raised to minus 1, meter raised to minus 2. And practically, the value of epsilon 0 is taken as 9 into 10 raised to minus 12 Coulomb square, Newton raised to minus 1, meter raised to minus 2. And hence, the value of K is 1 by 4 pi epsilon 0. That is 1 by 4 into 3.14 into the value of epsilon 0 is 9 into 10 raised to minus 12. And this will give the value of K as 9 into 10 raised to 9. That is, the value of K is 9 into 10 raised to 9, and unit is Newton meter square Coulomb raised to minus 2. Next is the permittivity of a medium. And when the charges are placed in a medium other than air or vacuum, that is, if the charge is placed in water medium or glass medium or any other medium, then the force between the charges can be represented by Coulomb's law. That is, F is equal to Q1 Q2 divided by 4 pi epsilon r square, where the epsilon is called the permittivity of the medium. And this epsilon can be represented as epsilon 0 epsilon r, or the epsilon r can be represented as epsilon by epsilon 0. That is, this epsilon r is called the relative permittivity or dielectric constant. And this relative permittivity can be defined as the ratio of the permittivity of a medium to the permittivity of a free space. That is, relative permittivity. Relative permittivity can be defined as the ratio of the permittivity of the medium to the permittivity of free space. And it is also called dielectric constant. Therefore, the Coulomb's law can be represented as F is equal to 1 by 4 pi epsilon 0 epsilon r into Q1 Q2 by r square. And this is the general form of Coulomb's inverse square law. Next, consider the Coulomb's law in two different media. The first, the Coulomb's law in air medium, and the Coulomb's law in a different medium. For the air medium, the Coulomb's law can be represented as 1 by 4 pi epsilon 0 Q1 Q2 by r square. And for the medium, Coulomb's law can be represented as 1 by 4 pi epsilon 0 epsilon r Q1 Q2 by r square. Therefore, the F air divided by F medium is equal to epsilon r. And this epsilon r is called the dielectric constant or relative permittivity. Thus, the dielectric constant or relative permittivity of a medium can be defined as the ratio of the force between two charges when placed at a distance in air to the force between the same two charges when the two charges are placed at the same distance apart in any medium. Next is the unit of charge. The SI unit of electric charge is Coulomb and is denoted by C. If the charges Q1 and Q2 have unit values, that is Q1 is equal to Q2 is equal to 1 Coulomb, and the distance of separation between the two charges Q1 and Q2 is unit value, that is R is equal to 1 meter, and the permittivity of the medium, it is given as 1. Then from Coulomb's law, F can be represented as Q1 Q2 by 4 pi epsilon 0 epsilon R square. Here Q1 is 1, then Q2 is 1, and 1 by 4 pi epsilon 0. It has a value of 9 into 10 raised to 9, and then the force will be 9 into 10 raised to 9 into 1 divided by 1 into 1 square. That will give 9 into 10 raised to 9 Newton. That is, if two charges of 1 Coulomb, they are separated by a distance of 1 meter in an air medium, then these two charges would repel with a force equal to the weight of million elephants, taking the mass of an elephant to be about 10 raised to 3 kilogram. Next is the Coulomb's law in vector form. If Q1 and Q2 are 2 point charges which are placed at the points 1 and 2 respectively at a distance r apart in a medium, then according to Coulomb's law, consider the force acting on the first particle or first charge due to the second charge. That is, the force on the first one due to second one, it can be represented as F12. That is, the force on the first charge due to the second charge. It can be represented as K into Q1 Q2 by R square into unit vector R, where this unit vector R is a unit vector which is pointing from the second particle or the second charge to the first charge. That is, the direction of the R21 is, this is the direction of the R21. That is, this unit vector, it is pointing from the second to the first. And similarly, the force acting on the second particle due to the first one can be represented using the Coulomb's law as F21 is equal to K into Q1 Q2 by R square into the unit vector R12, where R12 is the unit vector which is pointing from the 1 to 2. And here, considering the unit vectors R21 and R12, that is, R21 is pointing from 2 to 1 and R12 is pointing from 1 to 2. Therefore, mathematically, it can be represented as R12 is equal to minus R21. Therefore, the two force equation becomes, that is, the force acting on the first particle due to the second charge and also the force acting on the second charge due to the first charge. And it will be F12 is equal to minus F21. That is, the force acting on the first charge due to the second charge will be equal and opposite to that of the force acting on the second particle due to the first charge. Then it shows that the Coulomb's law obeys the Newton's third law of motion. Next is the limitations of Coulomb's law. And the first limitation of Coulomb's law is that it is applicable for charges at rest. And the second limitation is that this Coulomb's law, it holds good only for point charges. And this Coulomb's law, it acts along the line joining the center of two charge carriers. And the fourth one is that the separation distance cannot be specified accurately in case of charges with arbitrary shape. And the fifth one is that all experimental results indicate that this law is valid for distance from 10⁻⁻15 to several kilometers. And these are the main limitations of Coulomb's law. Next is the comparative study between Coulomb's law of electrostatic force and Newton's law of gravitation. And the motivation behind the Coulomb's law was Newton's law of gravitation. And according to the Newton's law of gravitation, every particle of matter in the universe attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And like Coulomb's law, we can represent this gravitational force as F is equal to G m1 m2 by r square. And in the case of Coulomb's law, we have studied a constant K. This constant K, which depends on the nature of the medium in which the charges are placed. But here, analogous to this constant K, in the case of Newton's law of gravitation, and this constant is called universal constant. It is also called universal gravitational constant. And this constant, it is a universal constant and not depends on any medium. And hence, both the Coulomb's law and the gravitational law have some similarities. At the same time, they have some differences. First similarity is that both the forces act along the line joining the centers. And the second one is that both the forces are derived from inverse square law. That is, in the Coulomb force also it depends on 1 by r square dependence. In gravitational force also we can see this 1 by r square dependence. That is, both the forces are derived from inverse square law. And the differences is that the electrostatic force can be either attractive or repulsive. But the gravitational force is only attractive in nature. And the second difference is that the electrostatic force is a medium dependent, but the gravitational force is independent of the medium. And these are the similarities and the differences of electrostatic force and gravitational force. Next is a problem to compare the Coulomb's law of electrostatic force with the gravitational force. The question is, in the case of hydrogen atom, in which the electron and proton separated by an average distance of 5.3 into 10⁻⁻11 meter, calculate the electrostatic and gravitational force. The electrostatic force of attraction Fe is equal to Q1 Q2 by r square into 1 by 4 pi epsilon 0. The value of 1 by 4 pi epsilon 0 is 9 into 10⁻⁹. And the charge of an electron and a proton have the same magnitude, that is 1.6 into 10⁻⁻19 Coulomb. Then Q1 is equal to Q2 is equal to 1.6 into 10⁻⁻19 and R is 5.3 into 10⁻⁻11. On solving, we get the equation as 8.1 into 10⁻⁻8 Newton. Similarly, the gravitational force between the electron and the proton is, the gravitational force is given by G m1 m2 by r square. Here, the gravitational constant G is 6.7 into 10⁻⁻11 and the mass of an electron is 9.1 into 10⁻⁻31 kilogram and the mass of a proton is 1.67 into 10⁻⁻27 kilogram and R is 5.3 into 10⁻⁻11. On solving, we get the gravitational force as 3.7 into 10⁻⁻47 Newton. then the ratio of Fe by Fg is equal to 2.19 into 10 raised to 39. That is, the electrostatic force is 10 raised to 39 times greater than the gravitational force.